Kia ora. Welcome to the third lesson for this remote learning week. This one hopefully won't feel as intense as the previous one that I just did. I'm hoping it'll also go a lot quicker because in this example, basically you're going to get another kind of example of the galvanic cell. In this case, it'll be a little bit more complicated because we will be looking at the inert electrodes. The other thing we will be doing is we will be looking at something called the standard cell diagram. This isn't something that's going to be assessed, but useful for you guys to know because it's part of understanding that chemistry language. So just building that kind of science literacy. For your mahia, I want you to basically do a compare and contrast between the galvanic and the electrolytic cells. Think about their similarities, think about their differences. I would suggest you do this as a Venn diagram because it's useful to see it. This is basically the question we're going to give as the final section of the internal, and you need to answer this in order to get the excellence. If you are just trying to get achieved or a merit, you don't even need to do this comparison. So take a moment, pause, and get that done. All right, so hopefully you guys have finished that. I am not going to go through it because I think it's quite tedious. Actually, I have these images drawn, so I might as well use that. Let me just do that. All right, so I have both of these images drawn, the general galvanic cell. This one was the do now from the other day with the general electrolytic cell. Key differences is that one has one beaker, the other one has two beakers. The galvanic cell is also separated both electrodes, whereas the electrodes are in the same cell for the electrolytic. The other kind of key difference between these two is that one requires energy, the other one produces energy. This one has a salt bridge. They both do have the same anode and cathode, and with that anode and cathode, you still have the same half reaction occurring, so oxidation at the anode and reduction at the cathode. So that's something that's still the same. But you would note that one of the differences between the two is that the charges are opposite, depending on what we're talking about. Those are the kind of key things that I think about when I'm thinking about these two examples. I mean, one of them has a salt bridge, the other one doesn't. But the reason why I want you guys to learn setup is because the setup is really useful then for when you are explaining the differences. Anyway, let's look at the more complicated galvanic cells and the standard cell diagram. So for our remote learning lesson today, basically we have a crash course video to show you. That crash course video is a really good summary, just to get you guys kind of recapping the whole point of the galvanic cells. It also revises the electrolytic cell, so you can really kind of see big picture-wise what we're doing with the redox this year. I will then start talking about the inert electrodes, and I will do another example galvanic cell with these kind of inert electrodes, so you guys can see it and just have another example as kind of worked. And then I'll talk about the standard cell diagram and how basically that works. It's really just a form of communication. And then lastly, you have some follow-up work to do. Again, we're still working mainly on that vocabulary when it comes to this lesson. The other thing that's kind of new to you guys will be the standard cell diagram. It's not actually on the marking schedule as something that we assess as a requirement, but I want to teach it to you guys because it will pop up in various sort of homework and examples, and chemists like to use it as a shorthand. So if we can give you the question in that shorthand, you can very quickly then practice the drawing and things like that. Anyway, here's your crash course video.
Ah, the controlled flow of electrons making possible laptops and phones and cars and pacemakers. Batteries, just like everything else in life, is just chemistry raised to the power of awesome. The kind of chemistry that happens inside of a battery is called electrochemistry because it involves reactions that produce or consume free electrons. Specifically, they are oxidation or redox reactions, the ones where electrons are exchanged. I've told you about redox reactions before, and if you haven't seen that episode yet, you should probably probably go watch that before you watch this. Don't worry, I will still be here when you get back. Now, when the flow of electrons from these kinds of reactions are sent through a conductor, like a piece of metal, it can be used to do all sorts of work. Like, for example, this kind of work. The amount of work that can be done depends on how strong the push or pull on electrons is between the two reactants. This is the reaction's electrical potential, but to its friends, it's known simply as voltage. Basically, if the voltage is high, each electron can do a lot more work than if the voltage is low. Many of the wonderful things in our modern lives are based on one simple premise: putting a device between the two halves of just such a reaction, the half that donates electrons and the half that accepts them. By harnessing that energy, a lot of the coolest things you've done today, up to and including watching this episode of Crash Course Chemistry, has been made possible. Part of what makes redox reactions so powerful, and powerfully excellent, is that they are complicated. Because in each reaction there's at least two things going on. There's a part of the reaction where the electrons are being released, and another part where they're being eagerly demanded. So when we deal with electrochemistry, we usually think of reactions in terms of half reactions. Let's start with the typical redox reaction that happens in this alkaline battery as an example. In here, elemental zinc is going to react with manganese dioxide, also known as manganese 4 oxide, to produce manganese 3 oxide and zinc oxide. When you break this down into half reactions, first you have elemental zinc with an oxidation number of 0 being oxidized to zinc 2 ion. At the same time, manganese 4 is being reduced to manganese 3. When we balance the half reactions, we see that 2 electrons are released during the oxidation of each zinc atom, and 1 electron is consumed by each manganese 4 atom. The water and hydroxide ions, by the way, come from a solution of potassium hydroxide, which is a basic or alkaline compound, which is why we call these things alkaline batteries. Now, if each of these half reactions occurred in contact with the other one, they'd just spontaneously go to equilibrium, releasing energy as a bunch of heat, which wouldn't be very helpful. So batteries are designed to harness that energy by isolating the half reactions from each other. This allows excess electrons to build up in the negative terminal, called the cathode, while an electron vacuum of sorts occurs in the positive terminal, or the anode. Electrons can then cross from one half reaction to the other only when we connect the cathode and the anode of the battery via conductors, so the current can be used to do work, which I can do by licking this 9-volt battery. Ah! In these batteries, the zinc is in the center, surrounded by a layer of cellulose that allows ions to pass through. The manganese oxide is in the outer layer that surrounds the zinc core, but the cellulose barrier doesn't allow the zinc and the manganese to mix. Alkaline batteries are a type of galvanic cell, which is generally defined as an apparatus that generates electrical energy from a redox reaction. Here's another example of a galvanic cell, one where the interesting part is the flow of whole ions instead of the flow of electrons. In this case, wires connect metal rods that are suspended in a solution. They're the anode and cathode here. What's noteworthy is that the metal atoms are actually consumed. They're used up from the anode rod as they're oxidized, and the metal slowly wears away. Meanwhile, the opposite happens at the cathode rod, where metal ions from the solution gain electrons and precipitate onto the cathode as pure metal, gradually growing larger. The circuit is completed by the wire, but also by a salt bridge, which is often a U-shaped tube that contains a salt solution that allows the metal ions to go from the anode to the cathode. So, now you know how batteries work, developing and transferring a charge using electrochemistry. But before any redox reaction can be used to text your boyfriend or girlfriend or whatever, we need to know how much voltage it can generate. Fortunately, all of those amazing chemists who have come before us have done a lot of the work once again. The voltage generated by many half reactions is already known and can be found in most textbooks or online. And as I mentioned earlier, voltage is really just a way of expressing the electrical potential of each half reaction, the difference between the chemical demand for the electrons in one half versus the tendency to lose them in the other. These measurements are done at standard conditions, which we discussed in the enthalpy and entropy episodes, and by convention, they are written as if the substance is being reduced, not oxidized. For this reason, the value is known as the standard reduction potential of a substance. To see how reduction potentials work in half reactions and combine in an overall reaction, let's consider a galvanic cell where zinc is oxidized and copper ions are reduced. Keep in mind that potentials are determined at standard state, 25 degrees Celsius and 1 molar solutions of the copper and zinc ions. Our cell needs to be set up under the same conditions, or the voltage will be a bit different than expected. The half reactions show more clearly what the electrons are doing. We can see that the zinc is oxidized and the copper is reduced. Now, all standard reduction potentials are measured relative to the reduction of hydrogen ions to hydrogen gas, which is set at 0. just as a baseline. When copper is reduced, for example, it generates 0.34 volts more than hydrogen does. So we say its standard reduction potential is plus 0.34 volts. The standard reduction potential for zinc is negative 0.76 volts, but because zinc is oxidized in this reaction, we can't use the reduction potential directly. Instead, as a general rule, when you convert a reduction half reaction to oxidation, the sign of the voltage is simply reversed. So the negative 0.76 volts for the reduction potential of zinc becomes positive 0.76 volts for the oxidation potential of zinc ions. And the electrical potential for the whole reaction, called the standard cell potential, is just the sum of the standard potentials of both half reactions. In this case, that would be 1.1 volts. Now I gotta point out here that the electrical potential of a redox reaction is related to its equilibrium constant. There's actually a way to determine the equilibrium constant from a measured voltage and vice versa. Both of these constants have a lot to do with the energy that the reaction can release, or its Gibbs free energy. But in brief, the higher the voltage, the more electrical energy can be produced. So if the voltage is positive, it means that under standard state conditions, the reaction will spontaneously go forward. If the sign is negative, the reaction will proceed backward. And it totally makes sense when you think about it that reactions like this are used to make battery cells. The reactions in batteries need to be spontaneous because their whole purpose is to release energy, not consume it. So what if we don't want to power a phone or a laptop or a toy shuttle? What if instead we want to plate an iron car bumper with chrome? This cannot be done with a spontaneous reaction. Instead, a different electrochemical process is needed, one that you've probably heard of: electroplating. This is done by immersing an object in a solution that contains an excess of ions of the coating metal. A bar of the coating metal, in this case chromium, is used as the anode, and the item to be plated, the iron bumper, acts as the cathode. When an electric current is applied, a redox reaction occurs in the solution and atoms of the coating metal are deposited on the cathode. This is essentially the opposite of a galvanic cell, known as an electrolytic cell, and it performs electrolysis, which uses electricity, electro, to do the breaking apart, lysis. In this case, molecules in the solution are being broken down so that the metal atoms can be deposited on a surface. Electrolysis is used for lots of other things too, like coating jewelry or flatware with gold or silver, refining metals, and separating mixtures of metal ions. Also, converting water into hydrogen gas and oxygen. So if you didn't already understand how much impact chemistry has on our daily lives, you certainly should be able to see it now. Not only are all of the materials around you made of chemicals, but even the electrical devices that power our lives depend on the reactions of electrochemistry. Thank you for watching this episode of Crash Course Chemistry. If you were listening, you learned that electrochemical reactions are redox reactions that we describe in terms of half reactions. You learned how an alkaline battery works and what's inside of it, what a galvanic cell is and how it can be set up, and how to calculate the voltage that can be generated by a half reaction, the standard reduction potential, and by the overall reaction, the standard cell potential. You also learned how electrolysis and electroplating work. This episode was written by Edie Gonzalez and edited by Blake DiPastino. Our chemistry consultant is Dr. Heiko Langner. It was filmed, edited, and directed by Nicholas Jenkins. Michael Ronda is our sound designer, and Thought Cafe is our graphics team.
Cool. So I hope you guys found that as a nice little recap. So when I talk about galvanic cells with inert electrodes, basically I'm talking about electrodes that are, let me get my laser pointer, that are carbon-based, or the other thing that it could be is platinum-based, because platinum is a very unreactive metal. When we use these inert electrodes, the reason why has to do with the fact that the oxidized and reduced species are in the same phase, aka they're both in solution. Or it could also mean that one of the species is not a solid. So say, for example, it's releasing a gas. The other thing that it could be is that one of the reagents or the products is a metal that's from group 1, and we know that the metals from group 1 are very reactive with water. So that's why we choose then these inert electrodes, which are made up of basically non-reactive material, graphite, platinum, those sort of thing. Before I do that though, I'm going to do some standard cell. This does not make sense in that order. Let me do the galvanic cell for this example here first. And then what I'll do is I'll do the standard cell and explain how that works. But this will be a good little refresher. Cool. So here's my galvanic cell. And in this case, my pairing is going to be iodine and also the permanganate with the manganese 2 ion. So let's say in this example, I am trying to, let's say I have both of these guys are carbon electrodes. And the way I'm going to distinguish the solutions is that in this solution, we're going to have the potassium iodide. And in this solution, we will have potassium permanganate as what's been dissolved. Cool. So what I need to then figure out is looking at these pairs, which is going to be the oxidation and which is going to be the reduction reaction. So that way I can start assigning work and going our way through it. So when I'm looking at this, I'm going to grab a different color. Let's do orange this time. So I'm looking for my permanganate. This is this guy over here. And I'm also looking for my iodine, which is right down here. All right. So I can see that my permanganate is going to be ranking higher. So this one must be reduced. And since it's reduced, I'm going in this direction. In this case, I have the iodide and the iodine. This has a lower number, and so that means ease of oxidation. That must have the oxidation reaction, so I'm going in that direction for it. So now that I've assigned things, I can start dropping things down. So if you guys remember, first thing I like to always write down is that I know this is a spontaneous reaction. Let's just get that ticked off right away. Cool. Next thing is that I need to figure out which one was the oxidation and which one's the reduction. So like I said, I figured out the permanganate is what's being reduced because I can see on the standard reduction potential, its standard reduction potential is higher. So that means ease of reduction, this one is going to get reduced. So basically, I'm going to write on this side that I know that this is the reduction reaction. Again, I'm going to give my general definitions. It must have gained electrons, and you could also write that it has a decrease in the oxidation number. Other thing I would need to then write down is basically the pairing and figure out what's happening. So I would be writing down that I know that MnO4 minus will be reduced to Mn2 plus. Again, I know that from looking at my sheet here, and I've identified that this is the reduction reaction, so this must be the product that I'm seeing, and then from that information I can figure out the observations. Other half of the reaction then, this must be the oxidation. This must mean that it has lost electrons, and or you could write down that you know that the oxidation number has increased. And again, if I use that resource sheet, I will see that the iodide is going to iodine. So that's what I should be writing down. Cool. All right, if I write down those things, I am done. This is me at the achieved level. I have nothing else I need to do. All right, let's go to the merit. All right, merit, if you guys remember, in this case, you are needing to calculate the E cell, so just kind of keep that in mind that you need to have that. You'll learn how to do that next week. Remember, the other thing for the merit is that you need to you need to have half equations and you need to have your observations. So I'm going to do the observations first because I find that a little bit easier. The first thing to note with the observations in this case is that they're slightly different because I'm dealing with things that are, in most cases, ions. So I would state that on this oxidation half of the reaction with iodide becoming iodine, I would notice, if I'm looking at it, iodine is becoming a brown kind of color. It could be aqueous. It might come off as bubbles. It's quite heavy as a gas, so I might have some bubbles. Otherwise, I would be noting that there would be basically a brown color produced. In solution, or you would say that there's a gas, and that is other than that, iodide, if I'm looking at it, is colorless. So I write down iodide doesn't affect color. Colorless soluble ion. So there's two observations there. My next observation then would be the permanganate. So what I would notice in this case, if I'm looking at the pairing, I know permanganate is the purple, and then it's going to colorless. So basically, observation-wise, with this solution, I would state that I know that solution becomes darker purple because more MnO4, or there's like an increase in that MnO4 concentration. Fourth thing I would write down, and this is now getting towards the excellence because I've now gotten O4, I would just be stating that MnO4 has no effect to the color change. So the decrease in Mn2 plus, sorry, I should say increase. Sorry, lighter purple. What am I doing? Doesn't change color. And no gases produced. Because it is a colorless soluble ion. So I hope that makes sense. I made a little boo-boo there. I think it's because I didn't do the equations first. All right, hopefully that is okay. I've done basically 4 different observations. I basically talked about each of the reactants and the products to state how does that affect the color change. Let's go do the half equations because that's going to help clear up my mind. So with these half equations, the one you have to think about is that they're a little bit more complicated. I'll do the iodide first. So in this case, I would have I minus becoming I2 and losing, in this case, 2 electrons, because that's a 2. So that's that half the equation done. The permanganate's a little bit trickier because I have the MnO4 minus. Remember that when we're doing these equations, Mn2 plus, I need to add water to balance it. That's why I'm saying we did the complex equations earlier, just to kind of refresh it. In that case, that's 4, so I need to add 8 hydrogen ions, and then when I'm looking at charge, that's positive 4, that's positive 2, so I'm going to need to add the 5 electrons to that side to balance that equation. So that's what that equation looks like. So I looked at the hard equations. All right, let's go towards the excellence then. So excellence is basically giving me my specifics to what's happening. and also kind of doing some annotations to what we are looking at. Other things I can do to kind of show my observations just occur to me. Showing that, it's iodine going to iodide, and that, that this is the brown color, whereas this is colorless. Do lots of annotations just to get your ideas across. In this case, you would see NNO4, which is purple, going to Mn2+, which is colorless. So all those are ways you can express how you know what's going on. All right, let's do the balancing. Let's do the justification. So in this case, I'm looking at a loss of 1 electron. Remember, that's 2 iodides. So if I'm thinking about in reference to 1, it's only 1. Oxidation number is increased by 1. Specifically, we see it going from -1 to 0. On this flip side here, when I'm looking at the permanganate, and I'm looking specifically at that manganese, it is gaining 5 electrons. That is only 1 there, so I know that this isn't a multiple in any way. Oxidation number has decreased by 5, because we've gone from +7 to +2. Cool. Next thing then is stating, E cell, it's positive, therefore spontaneous. And then the last thing you do is combine these half equations. So in this case, the closest number they're going to get to, if that's 2 and that's 5, is 10. So I need to multiply this equation by 5 and that equation by 2. So this is going to get real messy, and I'm going to try to squeeze it somewhere. I'll try to squeeze it up here. Yeah. All right. 10 iodide plus, and the electrons cancel, so you don't have to worry about them. 8 times 2 is 16 hydrogen. Plus 2 MnO4 minus. I'm just going to draw my arrow going down that way. 5 times 1 is 5I2 plus 2 Mn2 plus 8 H2O, and that should all balance out. So that's how I would do that electrolytic cell, galvanic cell. We won't give you something this hard, though. That's what I want to keep in mind. It's just mainly so that way you guys, in case it comes up, you know what to do. And if I want to annotate what's going on, just to show extra understanding, that's how my electrons are moving. That's where my negative ions are going. That's where my positive ions are going. Be mindful, we can flip this the other way around. Both examples I've shown you has oxidation on the left and reduction on the right. You can have it either or. You need to basically use that resource sheet to figure out what's what. Cool. All right, let's now backtrack to the standard cell diagram so you know what that is referring to. It is basically just a shorthand for us to communicate across what this cell looks like without having to draw this whole diagram. The thing to remember about these standard cell diagrams is that you are starting with the oxidation and you are going to the reduction. The way I like to think about it is, where are the electrons going? What's happening? What's changing? So in this example that we did yesterday, we had the iron becoming iron 2, and that's the oxidation reaction. So that's what I'm going to write down first. And then with the reduction reaction, we started with the copper 2 and we're forming copper, the metal. So on the ends of these guys should always be your electrodes. So I'm going to write Fe. You then draw a line. I'm going to write solid because it's in the solid state, to indicate that you're now done talking about the electrode. And instead now we are talking about the solution. Basically this iron is becoming iron 2. That is the oxidation half. And that makes sense when you think oxidation, loss of electrons. You draw 2 lines. The 2 lines represent that you are now talking about the other beaker, the other half of the cell. Write down what's gaining those electrons. So that's the copper ion, aqueous because it's in solution. Draw another line to represent that you are now talking about the electrode. copper solid. This, again, isn't part of the assessment scope. It's just useful because you're going to get homework questions and things that have that. And it's basically a shorthand for us to write this. All right, let's look at our complicated one. So when I have an inert electrode, it gets a little bit more complicated because now I need to actually factor in the fact that I have a carbon electrode. So we first write the electrode down, and in this case, it's an inert electrode, so that's all I write is carbon. I draw the line to represent that I'm now talking about the solution. In this case, we write the solution in the order of the oxidation and reduction process. So I am writing the iodide first, and then I'm doing a little comma to represent that this is the this is the oxidation. So this iodide is becoming iodine, which also happens to be aqueous. So that's my oxidation reaction. I draw the two lines to represent that I'm now moving on to the reduction reaction. Again, we're going to start with what's gaining the electrons. So that's going to be the permanganate. And that's aqueous. I'm running out of space, so I'm just going to write down, but it's the same rules. Again, comma to indicate that we're now talking about the other species. In this case, it would be the Mn2+, also aqueous. Another line to represent I am now talking about the electrode, carbon, solid. So obviously you'd have that all in one line, but I ran out of space. So that's what you're looking at. It's just an extra step because I need to be mindful that instead of having my electrode made up of what is being oxidized and what is being reduced, I have a carbon electrode instead, or a platinum electrode instead, and instead the reductant and the oxidant are squished together with the product that it's making. So that's what we're referring to when we say the standard cell diagram, and you'll be expected to write this on your homework, but not on the assessment. All right, so here is the follow-up work to do. So if after this lesson you feel kind of shaky on the material, do SciPad pages 62 and 63. That one is just practicing that standard cell diagram, and because it's SciPad, it's going to actually scaffold it for you, or at least give you some more background information instead of just tossing you into the deep end. The ESA 25B is going to toss you into the deep end. It basically says, here is an example statement, and you need to draw the standard, or you need to write the standard cell diagram. You will need the resource sheet to figure out what the products are. They are kind, and they do tell you what is the oxidation and what's the reduction half, but you still need the resource sheet to figure out the products, because the products are not always told to you. This actually, the ESA 25B, is really good if you want to practice doing the galvanic cell drawings and full write-up, because they're all examples of galvanic cells. So feel free to extend that and use it as more galvanic cell write-up practice. Last thing then is for the SOAR SciPad pages 67 to 69. These ones are more challenging than the ESA guide because they do not tell you which is the oxidation or reduction reaction. So like the ESA guide, unlike the ESA guide, you will need to use the standard reduction potentials to figure out which is the oxidation, which is the reduction, and then you're going to also use that to figure out the pairs and what you'd expect to see happening. This one, on top of that, will ask you to justify the redox reaction, which again is really good because if you want to get that merit or excellence, we are expecting that justification and those equations. So that's why I've differentiated it in that way. So just to summarize what you guys should have gotten from today, and basically what you should feel by the end of this week, is a really solid understanding of galvanic cells. You should be able to do them if they are basically the metal and the cation pair, or if they have two components that are aqueous or aqueous in a gas. Basically, you should be able to do it with the inert electrodes as well, and you should be able to shorthand all of this into a standard cell diagram.